So now let's continue with the case 2. In the previous case, we had studied about the effect of refraction when observer was in the rarer medium and the object was in denser medium. Now this is reverse the case that we had already studied, but some things are going to remain same, like we are going to say that wherever the object is present, from it the incident rays are going to come out, and the incident rays, if they come out, that medium is always medium number 1, so we'll give the refractive index as eta 1, and wherever the refracted rays they go, that medium would be referred as medium number 2, and medium number 2 will be always having refractive index eta 2, right people? And here again, this derivation is strictly for small angles and you cannot use it for larger angles. That means angle less than 1 degree, for such an angle this derivation is true. Otherwise you will just have to apply the Snell's law and carry on with the numerical problems. So here what do we have is, here is the water, and then I'm going to show a fish in the water. Now it's a very small tree, just assume a small tree, and then there is a fly. Let's call this fly as F. Now this fly is at some height above the surface. Note that in both the derivations, the distances are supposed to be measured from the surface. So two very important things. This derivation is only for small angles and all distances are measured from the surface. So that means this fly is at a distance HO, which is called the real height. Now from the fly, the rays are going to come out like this. Actually the light rays, they do not come out of the fly, but this is the reflected light from the sun, correct? Okay, now this light ray is going to bend towards the normal like this, and then there is a fish which is over here, and finally the ray, refracted ray, will go into the eye of the fish. Now wherever we have incident ray, we are going to call that as eta 1, and we have refracted ray over here, so we are going to call this as eta 2. Refractive index of this medium as eta 2. We know that refractive index of air is 1, but still if we are given some another medium, we can say that this refractive index is eta 1. So finally in the numericals you can put eta 1 as 1 if this is air, correct? So this is the object and this is the observer, and the refracted rays will always go into the eye of the observer. But finally the fish will feel that the rays are coming from here, because as discussed earlier, our brain, all living organisms brain, they don't understand that this is refraction. We understand that this ray is coming from something which is behind over here, so we feel the image of the fly as here. Now this distance, I'm going to call this distance as hi, and now this is real height, that was depth, now this is height. So this is hi, this is real height, this is apparent height. Now let's see the angles over here. I'm going to extend the normal a bit. This is angle of incidence, people. This whole angle is I. So as you can see that this is an alternate angle, so this angle is also I. Now this angle is R because this is angle of refraction. As you can see that these two are vertically opposite angles. This angle and this angle are vertically opposite angles, like this and this, so vertically opposite angles. Again Z formation over here, so this angle is also R, alternate angles, correct? So since these two are parallel, so this angle is R, this angle is also R. Now I'm going to call this distance as X. Now I'm going to apply the Snell's law. Now applying the Snell's law, let me first of all write it down. HI HO real height, this is apparent height, right? And now eta 1 sine I, that is equal to eta 2 into sine r. So that will be our eta 1 into sine I, that is equal to eta 2 into sine r. This is our Snell's law. Correct? Now what we are going to assume is all angles are small. That means we assume that all angles are less than 1 degree. Now we are going to change this from eta 1 sine I to eta 1 tan I, that is equal to eta 2 again tan r, because we have already studied that when all angles are small, sine theta is equal to tan theta is equal to approximately theta, right? So if you are unaware, let me write it down somewhere over here so that you don't get confused. When angles are small, sine theta is approximately equal to tan theta is approximately equal to theta but in radians. Correct? Okay. But for this, the angles has to be very, very small, approximately less than 1 degree or maximum 2 degree. Correct? Okay. Fine. Now, if you assume this triangle, in this triangle, tan I is equal to perpendicular upon base. So that means eta 1 into tan I, that is equal to x upon HO, that is equal to eta 2 tan r. So from this bigger triangle, x upon HI, again xx getting cancelled, so I am getting the same relationship HI upon HO, that is equal to eta 2 upon eta 1. Again a very important relationship, but this time people don't get confused that eta 2 is refractive index of the denser medium. In the previous case, it was the refractive index of the rarer medium. So why I am using this eta 1 and eta 2 like this, like wherever you have incident ray, eta 1 should be used, and wherever you have refracted ray, eta 2 should be used, because for different cases, just remember one formula, HI upon HO is equal to eta 2 upon eta 1. Correct? So whether the object is in rarer medium, denser medium, you just have to remember one formula, HI upon HO is equal to eta 2 upon eta 1. But eta 1 and eta 2 should be remembered like this, which I told you. Correct? Okay. Now eta 1 is here the refractive index of the rarer medium. So our derivation is ready to go. Now people, just remember one thing, that you cannot use this derivation for bigger angles, and remember that all distances are measured from the surface. So hopefully people, you have enjoyed my explanation. If you have not subscribed to my channel, please do that, and if you have any doubts, please do comment in the comment section. Thank you for watching the video.